All right, let's go ahead and try this out. So first we'll go for the posterior distribution, right? So so what we need to do is we're going to say, our posterior is equal to the likelihood times the prior divided by the marginal, right? Okay, so our prior distribution will look like this. We can say P, which is going to be the probability of heads, this is technically something like that. Okay, so we can say the probability of heads, it can either be the heads coin, fair coin, or tails coin. Okay, so this can be 0.8, 0.5, or 0.2. Okay, so we've got three possibilities for what P is, and because of this, we've got two are regular fair coins, and plus one heads coin and one tails coin. This is going to be 0.25, 0.5, and 0.25. Okay. I don't even know if trick coins exist in the real world. I think this is kind of just an imaginary thing. All right, it's like a unicorn. We can imagine it, but I don't think they actually exist. Okay, and so so this is what we have. All right, our likelihood for our data will be 10 choose 7, whatever P is, raised to the 7th power, and 1 minus P raised to the 3rd power. Right? So this is what we've got. All right, so far so good? Okay, so now it's just a kind of matter of plugging things in. The marginal is going to be the sum of the numerators. So really we just have to worry about all right, so so we'll do kind of the probability that P is equal to 0.8 given our data is, I will just write, is going to be proportional to 10 choose 7, 0.8 to the 7th times 1 minus 0.8 to the 3rd times the prior of 0.25. Okay, so I gotta punch this into the calculator. What's that? 0.050. 0.050 what? 0503. Okay, great. Okay, I mean, I don't know if that's going to present a problem for anybody here. All right, and P is equal to 0.5 given our data is proportional to 10 choose 7, 0.5 to the 7, 1 minus 0.5 to the 3rd times 0.5, and we get something else here. Okay. 0.0586. 0.0586, and then this thing's going to be really small. 0.2 given our data is proportional to 10 choose 7, 0.2 to the 7, 1 minus 0.2 to the 3rd times 0.25, and this is 0.00 something something something. What is it? 00196. 00196. Yeah. Okay, great. All right, so that's what we have. We're going to sum these. Okay, the sum will be our marginal. So actually, maybe I don't even want to write this out. So our marginal will equal whatever this is summed up to be. I want to pull up my calculator somewhere along the way. Where are you? Okay, there it is. Okay, so I'm going to do 0.0503, oops, plus 0.0586 plus 0.00196. Okay, that's not helpful. Okay, so I get my marginal is 11,086. Sure. Okay, and so therefore, I'm going to divide all of these by our marginal, 0.11086, to get our posterior probability. Okay, so I get 0.0503 divided by 0.11086, and I'm getting...
Last one, I think, is 0.000196.
Oh, 0.000196, okay. Yeah, no problem. All right, let's try this again. Okay, 0.0503 plus 0.0586 plus 0.000196, okay? So, I mean, if on an exam or something you have a problem similar to this, and you show all of your work, okay, and you just left out a 0 here and it kind of throws off your answers, like, we can give you partial credit. Like, you'll probably lose like 1 or 2 points for just, you know, this mistake, and as long as everything else makes sense and it shows that you understand what you're doing, we're happy to give you the partial points there. But if you show no work, then you know, we're in a sticky situation that we don't know if you know what you're doing. Okay, so 109.096, 09096, 09096. Okay, so let's try this again. All right, so let's okay, 0.0503 divided by 0.109096. Okay, so we get 0.461. Okay, so yeah, that's close enough. All right, so we got that, and then we'll do 0.0586 divided by 0.109096, and we get 0.537. And then the last one, 0.000196 divided by 0.109096. This is going to be really small. 0.002, I think. All right, so because of rounding issues, it doesn't exactly add up to 1. It adds up to 1.001. But it's okay, all right, because of rounding issues. So this is our posterior distribution. Is that good? And so this would be, so our posterior would be P and kind of the probability of P. We have 0.8 has a value of 0.461, 0.5 has a value of 0.537, and 0.2 has a value of 0.002. Okay. Is that good with everybody? All right. Any questions? No? We're good? Okay. And then, all right. And then, so now the question, the remaining question is, okay. Given this probability distribution, what is the probability when you do a trick that the coin will land heads twice in a row? Okay, so now, oops, so we're going to do this. Okay. So now that we have this probability distribution when we do a trick, what's the probability that the coin will land heads twice in a row? So the probability that the coin basically heads twice in a row is equal to p squared, right? So you just take the probability of landing hands and you just square it. Okay. So, so the answer is going to be basically the expected value of f of h of x, okay, And for the continuous case, it's the integral, but now it's going to be the sum of basically h of x times f of x. There's no dx here, okay? Basically for all, I guess you would do x sub k or something. For all k equals 1 to k, for however many categories you have or discrete cases you have. Okay, so we've got 3 of these cases, and so we're going to just have the sum of basically, we're going to plug in 0.8, and we'll square that. We're going to multiply that by 0.461, and then we're going to take the next one, 0.5, and we'll square that, and we multiply that by 0.537, and we do the last case, 0.2, we square that, and we multiply that by 0.002. Okay? If we had the continuous case, then we would have to do an integral. Okay? But with the discrete case, you can just take each case and then do the multiplication of the sum. This is for discrete f of x, and k is basically the big K is number of categories, or I guess number of discrete outcomes, I should say. Okay, I don't know what this is. All right, so we'll multiply this. We got 0.36 times 0.461 plus 0.25 times 0.537 plus 0.04 times 0.002. Did I mess something up? Oh, 0.64, yeah. Sorry. Okay, so 0.64 times 0.461 plus 0.25 times 0.537 plus 0.04 times 0.002. Okay. All right, 0.42937. Okay. All right. And that's that. Okay. So this is simple enough that we could do, we can do it kind of analytically, and this will give us our kind of our exact Bayesian answer, all right? And we still don't know, okay? So here's the thing. At the end of the day, we still don't know which coin this is, okay? The coin that we've been flipping, we flipped it 10 times and we got 7 heads. We don't know which coin it is. It could be the fair coin. It could be the heads coin. It could even be the tails coin, and we just got this really weird outcome, okay? Probably not the tails coin, okay? But which coin it is still a mystery to us, okay? We can gather more data, and our posterior distribution will become more and more extreme, kind of revealing one of these to be the case, right? If you do it 1,000 times, you're probably either going to get something around 500 heads or something around 800 heads or something around 200 heads, okay? And in that case, it'll be very clear which coin it is. But right now, after 10 flips, I guess you could be in the corner and you could still be flipping the coin, trying to figure out which coin you've got in your pocket, but that's unknown. But the key here is that in Bayesian statistics is which coin it is, like it is of interest to us, but we are also comfortable saying that it's a random variable. It's got some probability distribution, okay? But we're still not quite sure what it is. But even though which coin it is a random variable, we are still able to do some calculations based on this, okay? And this is neither, this answer, 0.429, is neither the answer for getting 2 heads in a row for the heads coin or the fair coin or the trick coin. It's some kind of like compromise between the different possibilities, okay? So it's still unknown, okay? kind of the coin, like which coin it is a random variable, okay? Okay. Even still, we can do calculations about kind of future probabilities. That depend on, and I'm going to use kind of theta as kind of the generic parameter term, okay? Depend on theta, or any parameter, okay? And this result, 0.429, is a compromise kind of between the possible outcomes. Okay. Doing something like this from a classical standpoint would be will lead to some predicaments, okay? Because in the classical maximum likelihood estimation, you would say kind of the probability that this coin will land heads is 0.7. Okay, based on the data we have, the maximum likelihood estimate is 0.7. But we know, based on these coins, that it cannot actually be 0.7. It's either going to be 0.8 or it's going to be 0.5, and so you might have to do something with that. Kind of the choices that you have, 0.8 is going to be the most likely outcome. But then, there's a possibility that it's not. Okay, do we feel okay about this? All right. Let's just talk about what if we wanted to do something like this in R. Okay. So in R, again, we can do the calculations directly. It's simple enough to do it directly. We could calculate kind of our. I made a mistake up here earlier. Like we could get the posterior probabilities. This is what I got in R here, the R calculations. We could also do kind of a Monte Carlo approximation too. Okay. All right, how can we simulate a discrete random variable in R? Something like this, right? So our prior I guess, so we've done the calculations and we have the posterior. So our posterior distribution is basically this. Okay, so this is our posterior distribution. How do we approximate? How can we simulate this in R? So if we wanted to get kind of the expected value of f of h of x as in this case, we're going to approximate it. Monte Carlo integration, but it's not really integration. It's whatever the discrete case would be. So simulating a discrete distribution, we can use what? Random numbers, yes. Okay, so I mean, there's a few ways you can do it, right? One is, oops, That's not what did I do? That's weird. Okay. So one is you can do like R-unif, right? This is not the recommended way to go, okay? So we can do like X as R-unif, a random number. And then, so this is for P equals 0.8, this is P equals 0.5, and P equals 0.2, right? So one possibility is you can do this. This is a terrible setup, but you can kind of transfer this to the number line, okay? And you can say, okay, if the number ends up between 0 and 0.4612, this is kind of the range where we're going to get 0.8, and this will be, I guess this will be 0.998, and this will be the range where it gets 0.5, and this will be the range where it gets 0.2. Does that kind of make sense? So you could do this, right? And that will work. That will work. Okay. So one is you can say if x is less than what was my first number? 0.4612. Then you would write p will equal 0.8, and then you do next if x is less than 0.998, and I guess I could do the double and greater, and x is greater than 0.4612. Maybe I have to do greater than or equal. Okay, then p equals 0.5, and if x greater than or equal to 0.998, p equals 0.2. Okay? So that's one possibility. Okay? And that would work. That would work. Easier method would be to just use sample, okay? And your x is going to be 0.8, 0.5, 0.2, and then you can just say I want one of these things, and then you say probability is equal to 0.4612. What's the other number? 0.5369, 0.5369, and the last one 0.0018. Okay, and that will also work. That will also work. So here I can just kind of demonstrate. I can say P is going to be the result of something. Oh. Sorry, we need that. Okay, so you're going to sample 0.8, 0.5, 0.2 with, that's weird. Did I do something wrong? Okay. No, we want the number of items to, and the number of items to choose from. Okay, sorry, you were right. So we want, did I do this wrong? Okay, it should work. Incorrect number of probabilities? Doesn't add up to 1? Darn it. What is the sum of this? All right, we got to fudge some numbers here then. All right, which one is the one that I should fudge? All right, we're going to round this one up to, it should be rounded up to 0.47 anyway. Okay. Is that still giving me an error? It's giving me the incorrect number of probabilities. What am I doing wrong? I Okay, maybe I had it right in the first place. Let's see. And maybe I do need to do replace equals true. Why am I having so much trouble here? Okay, I think it's worked. Let's just create a histogram of P. Did not work. Okay, that looks correct. Thank you. All right. The easier method that I struggled with right here. Okay. I guess you have to include replace equals true and the vector of probabilities there. Okay, so that's that. And then if we wanted to do it the other way, we can do for I in 1 through 10 to the 5, and then we would do this. And then I guess we would have a, I'll call this P2 sub I, we'll just throw in P. Right. I think this will work.
Do you need to define P2?
Do I? Oh, I do need to define P2, yeah. We'll just call this numeric 10 to the 5, okay. So it takes a little bit, and then we'll create a histogram of P2, and we hope this looks the same. It looks, did we not get any 0.2s? That looks like, let's see, tally P2. There's no tally function or a table. Okay, no, that looks about right. Okay, so we got that for there, and then let me just call this P3. And if I do table P3, we're getting something similar. Okay. Okay, so that's good. And of course, so then if you wanted to then do your Monte Carlo integration, once you have your vector P3, you would take, you would do P squared, I guess, whatever your vector is. So in our case, I've got P3 squared, and I'm going to multiply it by, no, I just take the mean of this, okay? So the mean of, I've got the mean of P3 and I've got the mean of P2, and we square it, the mean of just h of x, okay? So approximate using this. So this here is basically the mean of h of x, okay? And then and this will approximate this because in here this is x being drawn from our posterior distribution. Okay, and so what we're hoping for is that this will be close to the solution that we found earlier, which, what was it, 0.429 or something? All right, so we're hoping for something close to that. Okay, we get 0.4289, and if I take the mean of the other one, P2 squared, yeah, we get something very close, 0.4300. Okay. All right, and again, in the discrete case, you can just go directly and get the answer. But again, the beauty of this is that you can have these continuous distributions, which would normally require you to work out a complex integral, okay, as we saw on Monday, where we wanted to do it for the beta distribution, and this would be quite difficult, okay? Thankfully, R has pretty good capabilities to generate random numbers from different distributions. And if you're in a situation where you've got conjugate priors, okay? You got to do a little bit of algebra and manipulation to do your likelihood times your prior, and you get some resulting distribution. But a lot of those things with conjugate priors, you can kind of reformulate into some other regular old distribution, okay? So with the beta and the thing, the posterior ends up being a beta distribution. In some of the other situations, you have gamma distributions. And R can generate values from those distributions, the beta distribution, the gamma distribution, the normal distribution, all of those things. And so those work out, okay? On Friday, we will start talking about what do we do if the distribution we're working with is not one of the built-in distributions in R, okay? So what do we do if the result that we get has this weird PDF, okay? So the result will always have some kind of PDF, but maybe it's not one of these predefined things. Maybe it's not something that R has, okay? And so that's gonna occur in situations where you're not using a conjugate prior. If you've got a conjugate prior, the math is set up in such a way that that the posterior distribution will have, you know, a nice thing, right? So any of these situations, you have a beta prior and a Bernoulli likelihood, or beta prior and binomial likelihood. The result will be the posterior distribution will still be a beta distribution, okay? All of these things will have nice setups, okay? But in some situations you don't have a nice setup, and what do we do in those cases? We're going to have to talk about generating our own random numbers using the Monte Carlo approach, and we'll talk about that on Friday there. Okay, we'll see you guys in a couple of days.